What the heck?
Okay, so I just started. I've got to listen here and make sure that it works. We're on a 10-second delay here. But what I wanted to do is go into the next topic, which is the next module here, which is we're going to start focusing more on data structures. You know, it's data structures and algorithms. So as one part of that, I wanted to make sure that we're all on the same page here and ask how much of a review we need for, say, binary trees and binary search trees. So do we need a huge amount of review on those? Yeah.
You like a brief overview of the different kinds of search on a binary search tree? But
Oh, okay. So binary trees, of course, you have a parent, you have a left and right child. Right? Now, binary search trees, they have an additional requirement that the left key is less, right? So the key in the left child is less than the parent, and the key in the right child is greater than the parent. Now, what happens when you've got ties? Well, that all depends on what your implementation. You can prefer ties going into the right subtree. You can prefer ties being in the left subtree, as long as you're consistent about it. Or you can say, I'm not going to allow ties at all. And if I've got two things with the same key, and then I'll say, well, that's already in the tree. I'm not going to insert that. I can throw an exception. I can say no operation, whatever. Or if you have two things that have the same value, you can start to disambiguate it by saying that, okay, well, let's go off to some other criteria, a secondary criteria, a tertiary criteria, et cetera, right? And with the traversals, right? Traversals, of course, are pre-order, post-order, in order, and post-order. Right? You can also have a BFS, which we'll talk about later on when we talk about more generally graph traversal algorithms. Remember, we are online. Please ask your questions through YouTube today if you can, because I don't have Piazza up and running, sorry. But in any case, no, I haven't seen an actual question on Piazza for this course for several weeks. So anyway, pre-order traversal visits things in a root, left, right manner. Right? An in-order traversal will do it in a left, root, right manner. And a post-order traversal does it in a left, right, root manner, right? So it's only where you put it's always left and right. If you wanted to go right and left, fine, then just take your tree and reverse it, right? And and it's the exact same thing. It only differs where you do the root. So do you do the root first? Do you wait until you've explored the entire left subtree and then you've come back and then you do the root? Or do you wait for doing the root until you've explored the entire right subtree? Pre-order does it first, post-order does it last, and in order, as the name suggests, if you do that on a binary search tree, you will get an in order, you will enumerate all the elements in the tree in order, right? So do we want to see a quick example or not? Was that enough or, okay. All right. Enough, yes, or want an example?
that was enough.
Okay, all right. You may or may not want to represent eventually write your own tree node algorithms or your tree node class, at least in Python, especially for what we're about to do, because instead of giving you a full review now, and then finally also remember heaps. We will give a review on heaps after we've looked at today's algorithm. But in any case, I wanted to have a motivating kind of review by using trees to do something that you might not have seen before, called Huffman Coding. Right? So does anybody know Huffman Coding already? A little from modern algebra, maybe? Or oh, don't recall? Okay. Well, Codine Theory. First of all, we need some background here. So Codine Theory. Right? There are two branches of Codine Theory, and the father of Codine Theory is Shannon, Claude, whatever. And one branch is where you add redundancy to data or a signal to ensure that information is not lost over a noisy channel. So, for example, I mean, you could have wireless Wi-Fi 802.11g, HIG, whatever, ABC, and there is some probability that you'll have some interference, and that a bit could be flipped, right? So if you're sending 010101, one of those things could end up like a 0 could end up as a 1, or a 1 could end up as a 0, just because of background interference. Try it sometime. Take your computer, which is on Wi-Fi, and put it right next to a microwave and heat up a burrito at the same time. You will likely lose your wireless connection, right, if you're close enough, because they are almost on the same frequencies. And that microwave radiation interference, that most of it is blocked, most of it is harmless, even if it were not blocked. But when it's being, is it a magnetron that's generating that, right? That magnetron is generating that radiation. It's alpha-based radiation, so it'll never even penetrate your skin, I believe. But you don't want to sit yourself inside of a microwave, of course. But it's on almost virtually on the same frequency, and so it'll interfere, right? And that could just happen, randomly. Take a storage medium like a CD. If you get a scratch on it, right, then that could, destroy some of the bits. But if we add redundancy to it, or redundancy to the signal, then we can kind of reduce that or the chance that one of those bits will get flipped in the transmission. Yeah.
Is that similarity between like microwave radiation and like whatever stuff the computer's using? Is that why people think that like wireless computers or internet cause like cancer or something?
You're way beyond my knowledge there. I mean, certainly radiation is dangerous. Alpha radiation is not that dangerous because it's such high frequency that it doesn't penetrate the skin. Neutron radiation is definitely, stay away from that. Beta radiation is dangerous, but not at low levels. Stuff like X-ray radiation. It's all depends on the frequency and, of course, the power. I'm sure that alpha radiation could hurt you if it was high enough power and you were standing close enough to it. But I mean, the light that you see, that's radiation, right?
I know, I'm not concerned.
Right.
I know very strange people who have those concerns.
Okay, yeah, I don't know either. But anyway, so you can always add redundancy and get and reduce the amount of, or reduce the probability that you're going to miss information. For example, all you need to do is, instead of sending 1 0, send 2, or say 3. And instead of sending 1 1, send 3 1s, right? Now, what if I received 0 1 0, right? As this is called a code word. Likely an error occurred, because are either one of those my code words as far as my understanding goes? Nope. So which is most likely? Was it most likely that you meant to send a 0? Right? Again, the idea here is that you encode 0 as 3 zeros, then you send it over this noisy channel. And that noisy channel could be wireless, it could be a wired channel, it could be a storage medium like a hard drive or something like that, or a CD or something. And then over at the other end, say that we receive 0 1 0. Clearly, we were able to detect an error, because 0 1 0 does not match up with either of the code words that we're familiar with. In all likelihood, what did they mean to send over here at this other end? Probably 0, right? Because the probability that, what if it were 1 1 1? The probability that 2 bits gets flipped is even greater, is even less than the probability that 1 bit gets flipped, right? So the idea here is that a bit is flipped with probability p, right? And p is definitely going to be less than 1, right? In fact, it's going to be less than 1/2, right? Because if the probability that a bit gets flipped is, say, 99%, what do? You reverse 0 and 1. And now, the probability that a bit gets flipped is, you automatically flip them, right? And now the probability that a bit gets flipped is only 1%. So the noisiest channel is when you approach 50%. And then there's no way to distinguish, was it a 0 or was it a 1? And that's where you need to introduce all this redundancy, okay? So the probability that two things get flipped is even lower because it's going to end up being p squared. And since p is less than 1/2, but greater than 0, if it were 0, then we'd have a perfect channel, right? So it's between 0 and 1/2, so p squared is necessarily going to be even smaller than p, right? So the likelihood that you actually sent 1 is far less than the likelihood that you actually sent 0. So what you can do is you can take a parity, right? Or you can take a majority vote, right? If the majority are 0s, you probably meant to send 0. If the majority were 1, you probably meant to send 1. There's nothing to stop you from arbitrarily reducing that probability. The probability that half of them gets flipped now is going to be p to the n divided by 2. And as n approaches infinity, this will go off to 0. So you can always ensure an arbitrarily low percent, arbitrarily reliable data by simply just sending more bits, right? What's the problem there, though? Diminishing returns, exactly. And also, I mean, ideally, I'd only like to send 1 bit, 0 or 1. But if I've blown this up to 5 times, my 5G network is now a 1G network, right? So the idea here is, how can we encode enough redundancy by only adding, say, if we wanted to send n bits, what we'll do is we'll add log n bits of redundant info so that we can detect errors and or correct errors, right? The simplest and probably the most efficient scheme is just to simply have a parity bit. So if you wanted to send, say, 000010, right, you take the parity, you only add 1 more bit. It's going to be 0 if there are an even number of 1s. It'll be 1 if there are an odd number of 1s, right? So you can detect any odd number of bit flips. You won't be able to detect any even number of bit flips, but also you can't ever correct anything. But there are coding schemes that achieve this up here. Read Mueller codes, read Solomon codes. Those are kind of codes that are actually used on CDs in actual practice. And over network that use very sophisticated coding theory ideas and Shannon information theory, et cetera, to add redundancy. Add only a small amount of redundancy, giving you a larger guarantee of either detecting errors and or correcting errors. That's why you probably haven't ever bought a CD. Has anybody bought a CD? Are you of the generation that has no CDs? Okay, you have CDs, right? And have you ever noticed that you have a scratched up CD? If it's too scratched up, of course, it will skip and die. But small scratches, no problem, right? Because the encoding of that data using, I think, Reed Solomon codes can actually correct single bit errors. Right? So it is resilient for a lot of errors introduced into the encoding. Right? That's one branch. What's the other branch? The other branch is something that you are very, very familiar with, called compression. Right? Here we want to remove redundant information or unnecessary or reduce information for efficient storage or transmission. Right? So transmission. What are some examples? And this is the one that we're going to focus on. So what are some examples of compression algorithms or compression programs that you're well familiar with? WinRAR, okay. Or zip, right, basically, zip files, right? Or RAR files. RAR, something archive. What does the R stand for? There are also tar, that's a tarballs, right? Tarball is a tape archive. Nobody uses tape anymore. Well, plenty of people still use tape, but tar, etc. Right? Those are. What else have you seen? Maybe. How do you store images? You're taking an image, right?
Yep.
Oh.
Or JPEG.
Okay. JPEG, right? JPEG. How else could you store images? PNGs are use compression, right? Right. These are lossy compression, right? Compression. They either remove redundant, remove unnecessary data, or approximate the data. Right? JPEGs in particular are very, very interesting because they come up with these formulas that you can recreate the pixels from these formulas. And so, of course, it's tunable. The more compression you have, the more pixelated the image will look, right? That's because you're losing information. Likewise, things like, say, video, MPEGs or MP4s, right? MP4s, they actually take out redundant information. So it doesn't encode, if you've got a video and there's very, very little change from one frame to the next frame, they use what are called keyframes. So here's the keyframe where we refresh the entire image. But if this pixel over here doesn't change for the next 10 frames or 50 frames or something like that, we're not going to encode that pixel every single time. We're just going to encode changes in the pixel. So that 10 frames away, okay, now we need to encode a new keyframe or encode the information that was changed. And you can cut out a hell of a lot of data that way, right? Those are lossy compression standards. What we want to focus on lossless coding, right? You will tolerate no pixelization of your images. You will tolerate no loss of a word, right? If you are compressing a text file, for example, right? You don't want to lose every other word, right? You don't want to lose letters even that would lead to misspellings. So what we want is a lossless compression or encoding, right? Where every piece of data is recoverable. That we can expand it back out and get the original with no losses at all, right? And the one that we're going to focus on is going to be Huffman Coding, right? So Huffman Coding relies on the fact that English is very, very redundant. In fact, all languages are very, very redundant, right? English has a lot of redundancy, right? And non-uniform distributions on letters, right? So what does that mean? What are the most common letters? If you've ever watched the Wheel of Fortune, what are the letters that they give you for free? Right.
Vowels.
Vowels are way more common than consonants, but what about consonants themselves? R, S, T, L, E? What are those the free letters? Nobody watches that. I haven't watched it in years either, right? Are far more common than, say, Z or Q, right? And so here's the idea. We won't encode letters using a fixed length, that is block, encoding scheme, such as Ascii. Ascii does this. Instead, we'll encode common characters with a shorter code word. And that is one word, code word. And less common characters with longer code words. And omit any characters that don't even appear. Right? For example, if you're encoding, if you are compressing a document and there are no Z's at all, why bother encoding that letter? You're only going to encode the information that you have. Okay. So what do I mean by a fixed length encoding scheme? Ascii is like that, right? Ascii. If I encode the lowercase letter a, does anybody remember what that is? Okay.
I don't know.
Uppercase A, because I don't know. I don't remember either. But I do remember uppercase A. I think that's 65, right? And so that's going to be how many bits? 64, 32, 16, 8, 4, 2, 1, and then there's this extra 0 over here, right? For the extended ASCII character set, all code words are length 8. Right? Why do we need to use 8 when say the umlauts? We're not even going to encode those in our file. Why should we bother encoding those? Or Z, right? Capital Z now. That's going to be 26 letters away, so that's going to be what? 91, right? And so whatever that is, and that's also going to be, I don't know, 8 bits. Okay, right? 96, 91, right? Yeah. 26 letters in the alphabet. Right? Anyway, we don't have to worry about those small things, right? So why should A, which is way more common than Z, be encoded with exactly the same number of bits as something that's less common, like Z, right? Yeah.
So otherwise, you have to know when the end of a word.
Good. So let's take another example here. Let's suppose that we want to use what's called a variable length encoding scheme. So I'm just going to give you an example here. So 0, 0, 1, and 1, 0, 1, and 0, 1, 0. Right? Suppose that I only have a language with 4 symbols, DNA or something like that would be an example. And I've got these as my code words, right? These are 4 code words. Now suppose that I was sent a message, and it's just a streaming message, so it's this big chunk of data. Say 0, 1, 0, 1, 1, maybe. Okay. And then, well, here. Let's see. I usually come up with these off the top of my head, but I can't now. Right now, I don't know why. All right. Well, here's the simplest one. So suppose that I receive the following. Right? 0, 1, 0. And suppose that these are associated with A, B, C, and D. How would you decode this? D? That seems obvious. Right? Is that the only possibility, though? This.
True, it could be B and an A.
Yep, it could be B and then an A. Right? This is B, and then this part is A. How do I know that I sent you 1 code word versus 2 code words? This is what's known as a. This is not prefix free. Right? What that means is that some code words appear as prefixes of others. For example, A is a prefix of 0, 1, right, of B. What's another prefix? B, which is 0, 1, is a prefix of D, which is 0, 1, 0. Right? So you have ambiguity when you use a variable length encoding scheme. How do we get around that? We want a prefix-free variable length encoding. So let me go ahead and give you another example here. 1, 0, 0, 1, 0, 1, 1, 0, and 0, 1, 1, 0. What if I encoded A, B, C, D like this, with these 4 code words? Are any of those code words a prefix of another code word within this? Nope. And what we can do is we can assign, suppose that A is the least common character, right? Then that's going to be the shortest code word. D, say, is the most common, or least common, most least, I forget what I'm saying. This is the most common. Say that this is the least common. All right? Then what I can do is I can achieve some compression here by not using a fixed length encoding scheme. Because if I use a fixed length encoding scheme like, say, Ascii, everything is going to be 8 bits. And if you've got 1 million characters, well, that's 8 times 1 million. That's going to be 8 million bits. If I can compress that down by saying that I will encode every A with a single bit and everything else with a few more bits, right? Then I might be able to get the average code word length down, right? So what is an average code word length? Average code word length, right? Suppose that we have, suppose a symbol has a frequency, right? Or a probability that if you randomly select a character out of a file with 75% probability, then that character is an A, right? 75% of your characters are A's, right? Something like that. And then 0.1% of your characters are Z's or something. There's going to be a frequency. What we do is we take that frequency and we multiply it by the code word length. And then we sum up over all code words. And this will give us a compression ratio. In the very worst case, you could have a uniform distribution on all of your characters, in which case this becomes, say, a 1 over n, or n, and 1, I won't get that too specific there until we've gotten into the actual math here, but you can't do worse than Ascii already, right? Because it could be that you have a uniform distribution, every character is represented, and it forces you to have a block length encoding anyway, right? Okay? So can we do better, right? So the idea here, again, with Huffman Coding is that we're going to associate frequent characters with longer, with shorter code word lengths, and then we're going to associate rarer code words with longer code word lengths. And as an example, I'm going to run through a particular example here and visualize how we can build this code, and then we'll go ahead and codify it using pseudocode. Yeah, go ahead. Question?
I was more, I think I'm starting to see the pattern of how you're building each code word, because I was going to say, how do you know when building future code words that no combination of the previous code words will end up?
That's a good question on how we're going to do it, and
I see the pattern, but yeah.
we're going to have to develop an algorithm that shows you how. All right. So what I'm going to do is I'm going to just come up with 1, 2, 3, 4, 5, 6, 7. So A, B, C, D, E, F, and G, Imagine that these are all perfectly uniform rectangles. And G, there we go. And each one of them has an associated ratio with them, or an associated frequency. So 0.10 here means that 10% of the file that you're trying to compress consists of the character A. This is 15%, so B represents 15% of all your characters. C is going to represent, say, 34%. So C is the most common character in this particular file. The encoding is going to be different for every single file. Now, you're going to have basically the same compression ratio for English, and then you go over to another language or another piece of data, or like DNA or something, and you're going to have a different compression ratio. But whatever it is, suppose that this is an example here, right? So this is 5%, this is 12%, this is 21%, and this is 3%. Right? What I'm going to do is I'm going to build a binary tree. It's not a binary search tree, it's going to be a binary tree. And the idea here is I'm going to associate a code word with the unique path from the root of the tree down to any leaf node. These are going to be my leaf nodes here. Right? And what I'm going to do is I'm going to combine them in such a way that the least common elements are going to be deeper in the tree. What does that tell you about the code word length? If they're deeper in the tree, if it's associated with the path. Longer path means longer code word. If it's shallower in the tree, then it's going to have a shorter path and thus a shorter code word. So what I'm going to do is I'm going to start combining these, which are nodes, right? These are going to be my leaf nodes, ultimately. I'm going to start combining them by combining the least ones first. I want to make sure that I'm doing this right, so I want to look at my, oh, there we go. Yeah, all right. So I'm going to take the two least weighted ones over here. We call these weights. These are frequencies, but I'm going to call them weights from now on. So I'm going to take the two least weighted ones and I'm going to combine them to make a new tree. So what are the two least weighted ones here? G and D. Okay. I'm going to combine them and create a brand new tree. You know what? Can I make a perfect circle? All right. That one and that one. There we go. Now when I combine them, I'm going to, if the weight of a node is its frequency, then the weight of combined nodes is going to be the sum of their frequencies. So in this case, it's 0.03 and 0.05. So the weight of this node then becomes 0.08. Okay? How many trees do I have right now, by the way? There's one tree with 3 nodes. I agree with that. But each one of these is a tree with 1 node, right? You can call them seeds if you want, right? That's what some people have done in 156, right? Somebody many years ago in 156 gave me that, well, why don't we call them seeds? They go, that is a good name. I've never heard that before, though. So I stole it from him, and now it's mine. I have no idea who it was. So, all right. So I actually have five single node trees over here, and 1 3-node tree over here. So actually I have six trees now. I stop when I only have 1 tree left. Right? So let's continue. Combine the 2 trees with the least weight. So what's the least weight now? Certainly A. And what's the other one? The tree that I just created, because it has 0.05, or 0.08, excuse me. All right, so let's go ahead and put it over here and create a brand new node connecting this is a left child and this is a right child. All right, and now make sure that you update your weight here. The weight of that tree is 0.18. Next iteration. Which 2 do I combine now? B and E, okay. And this is 7.27. There we go. Okay, so I've got 1, 2, 3, 4 trees left. What on my next iteration, which two do I combine? F and this tree over here with 18. Okay. Combine that into 2. And now I've got 0.39. Okay, good. I am going to take this and move it down a bit. All right. So I've got 3 trees left now. Now which ones do I combine? This one and this one. And I'll do it here and then move everything down to give myself some room. New tree. And the combined weight here is 0.61. Okay. And then finally, I've only got 2 trees now left, so there's no choices left. So what should I do? Combine this one into a brand new tree up here with with 1.0, left tree, right tree, right? And there's my binary tree. Now, how do I make my code? I will associate going to the left child with 0, and associate going with the right child as 1. 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Right. Now, take a look at the unique path from the root to any leaf node. You'll note here that all the leaf nodes are associated with a symbol in my file, A, B, C, D, E, F, G. Right? So what is A? Here's my symbol. Here's my code word. And here's my length. Right? Okay. So A, there we go. Now I've got room. All right, so what is the code word for A? 1, 1, 0. 1, 1, 0. And by the way, the easiest way to build this stuff is to simply just start at the leaf and then just go up to the parent. And then reverse it. Or it doesn't matter, all these codes are going to be equivalent. If you take every code word and you reverse it, you still have a prefix-free code, and you still have the same frequencies and the same code word length, etc. Why? Because you can take this tree and you can reverse any node in the entire tree, right? You'll see that I did follow a pattern. The pattern that I followed was I always put the largest weight as the left child and the lesser weight as the right child. That's just because you'll want to be consistent about it when you go to program it and not just be random about it. Yeah?
I was wondering, if you have all of them sorted by weight or by frequency, starting from like the most frequent to the least frequent, what I noticed, what you did earlier was like how you made each of the prefix-free variable length encoding was you took what you had before, but then you added either a 1 or a 0 at the beginning of that.
I don't know if that was a pattern that I followed. That might have just been what I did when I wrote it down. But let's talk about prefix-free before we continue here. Is this code going to be guaranteed to be prefix-free? Yes. Why? How do you make these code words again? Let's try to see a pattern here. What about B? It's going to be 0, 1, 0. All right? That's certainly not a prefix of the other one. What about C? 0, 0. So the length here is 3, 3, 2. What about D? 1, 1, 1, 0. E? 0, 1, 1. F? 1, 0. And G? 1, 1, 1, 1. Right. What would it mean for one thing to be a prefix of another? So suppose that this is a code word. This is also a code word. Right? This is a prefix of this entire code word. Can you have that?
Mean one of the letters would have its own subtree?
Exactly. It would mean that one of the nodes associated with a letter or a symbol would be an internal node. And by construction of this tree, that ain't going to happen. Right? They're all going to be leaves. And because it's a tree, there's a unique path from any leaf node to the root node. So it's going to be guaranteed to be unique. It's guaranteed to be prefix free. And did we reach our other goal? Are the least common ones deepest in the tree? And the more common ones shallower in the tree? Yep. Why? Because of our greedy choice. We chose to combine the two least weighted ones at each iteration. And by that construction, we're going to achieve all three of our goals. Again, it's 4, 3, 2, and 4. Did we reach a good compression on this? Okay. So to understand what I mean by that, let's go ahead and copy this and give myself some more room here. Come on. Copy. Nope. Paste. All right. So this is the weighted code word length. All right. So what was the frequency again? A was, darn it, 0.10, 0.15, so 0.10, 0.15. The frequency of C was 0.34. D was 0.05. All right. E, F, 2.1, and then O3. Oh wait, what was F? F was 2.1. So what was E? 0.12. All right, there we go. So what is the average weighted code word length? You simply take the length times the frequency. Right, so this is 0.3. This is going to be 0.45. This is going to be 0.68, ... And you take the sum. And I don't want to do the math, so I'm just going to look at what it was. Unfortunately, I lost that. I think it's 2.53. Yeah, 2.53. All right. In other words, the interpretation here is that the average code word length is 2.53 bits. Now that's an average, right? There is not going to be any code word that is exactly 2.53 bits because you can't have 0.53 bits. This is just the average over the entire file. How many bits would we have required in the original file? Let's consider under Ascii first. 8. So already we've seen by cutting things out and removing encodings that we don't need, it's less than half, right? The number of bits in a fixed length encoding would be what? How many bits are required to encode 7 characters? Remember, it's A, B, C, D, E, F, G, right? So 7 characters. How many bits do you need to encode 7 things? You said 3. How did you get that number? Log?
Smallest power of 2 greater than 7.
Smallest power of 2 greater than, okay, there we go, yeah. Or log base 2 of the number of characters that you need to encode, and then you take the ceiling because you can't have fractional bits in a fixed length encoding scheme, right? So not only did we achieve encoding, a compression ratio better with respect to Ascii, but we also compressed it even with the best that you can hope for block length encoding. 2 ways of looking at this are, you could look at it as how much did you save? You cut off 0.47 bits on average. That leads to a 15%, roughly, compression ratio. So now if you go to a sale and they say that it's 20% off, it's 20% off, or are you paying 80% of the original price? Yes, both, right? How much are you saving versus how much are you now paying, right? And so you can also look at this as 2.53 divided by 3, and that's going to end up being an 85%, right? It's 85% of the original size. Okay, so you've cut it down by 15%. It's 85% of the original size. That's how you can, and it's 15.67 if you really care about that. But that's how much you can, that we've saved with this one example. In practice, you can get it down to about 60% of the original size with plain old English. If you've got a lot of redundancy, then you can cut it down even further. For example, XML data, where XML tags are repeated over and over and over and over again, right? That's not English, but it's even more structured data. You can probably get the compression ratio down even further. You can also get the compression ratio down even further by considering not just symbols, but by combinations of symbols. For example, in the English language, SH, TH, those are extremely common characters that appear right next to each other, right? What's a character that never appears next to each other? QQ, right? Or Q always has to be followed by a U. Is that a rule? Something like that, right? So anytime you see a Q, you can go ahead and just replace QU. You can replace that with just a Q with the understanding that there's a U behind it or something like. And so you can that's if you consider additional characters or blocks of characters, that's a generalization, and that's called Ziv-Lempel compression. And guess what's used in zip files? Ziv-Lempel. That's exactly the algorithm that is used in a lot of zip files. All right? Okay. So with only a few minutes left here, let's think about what the ingredients at least that we need to do this. Right? So we need, of course, nodes. Right? Those nodes will have to have a frequency. By the way, as a preprocessing kind of thing, if you're given a file to compute all the frequencies, what are you going to have to do? Go through the file, count up the number of A's. Go through the file, count up the number of B's. Go through the file, count up the number of C's, etc. I trust everybody can do that. Right? You'll need a frequency. You'll need parent, left, right, of course. For those leaf nodes, you'll need a letter associated with that, or no letter for internal nodes. Right? What else will you need? Table or map is what I would use of encodings. How are you going to get those encodings if you use a node? You're going to have to walk on the tree somehow, right? So if you're able to jump to a leaf, you're going to have some sort of walk algorithm back to the parent, right? So some sort of walking procedure in order to build those code words. You can do it with pre-order, post-order, in-order traversal if you really want to, but I would just suggest keeping track of the leaves and then just taking a trip up to the parent. And that's it. Right? What else? Well, remember this procedure that we used. I always chose the two trees with the least weight. What kind of algorithm or data structure might be helpful with that? I want a data structure that I can efficiently put those trees back into this pool of trees, like I did visually, but that I also want to efficiently pull out the one with the least weight, pull out the one with the second least weight, combine them, and then put them back into the pool.
What's stack?
A stack? Okay. That stack is, when I put them in, the weights are going to change. So I don't want it to be on top, right? I want it to be somewhere else because now it's probably not least anymore, right? I want the least things to be at the top of the stack all the time if I'm using a stack. You said a what? A linked list could be an underlying implementation for this. But what would you want with your linked list? What would you want at the head of the list all the time?
Minimum.
The minimum, right? You would want the available the second minimum as well at some point. But suppose you took off the minimum, and magically the next minimum appeared at the head of the list. You could take that off too. Combine them, throw them back into the linked list somewhere. Right? A what? A heap. Right? What does a heap do? It offers get min, right? Efficiently pulling out the minimum. It offers efficiently putting something in. Now, it doesn't necessarily go to the top, right? It could heapify down. So on Monday, let's have a review of heaps and a demonstration with respect to Python. Don't roll your own, don't make your own heap. It's right there. Right? But we will have to talk about the details, because every semester, hopefully not in this one, but every semester I tried to use the heap, but it doesn't work. Well, that's because you need to understand comparisons, right? A heap, suppose I got two things, 5 and 5, and I want to put them in the heap. What's a relative position in there? You're going to have a problem, because 5 and 5, that's the same thing, right? So how do you disambiguate ties like that? You need to look to something else. What if that something else is null? Then exception, right? So you have to be careful about those things. But otherwise, a heap will get you exactly what you want. In fact, all you're going to do is put stuff into the heap, take stuff out, tweak it a little bit, throw it back in the heap. Put stuff in, take stuff out, put stuff in, take stuff out. It sounds a lot like heap sort, right? And it's very, very similar to heap sort. You're just putting stuff in the heap and taking stuff out of the heap. Okay, yeah?
Could we take just a quick look at how you said,